Now we come to Newton's second law. This is a staggering thing in its implications and very, very difficult, really. But what students of physics learn somewhere in their course is that Newton's second law says F equals ma. And indeed, that's what it says. But that's powerful and not so easy. Let us see what Newton said for his second law. In the Latin, mutationem motus proportionalem esse vi motrici, but the Latin is a little old-fashioned, so if we look at the English, here it is. Change of motion is proportional to force applied and takes place in the direction of the straight line in which the force acts. So, let me demonstrate Newton's second law. Here I have two carts, a heavy one, a massive one, and a less massive one, and they are connected with a pseudo-spring, an array of rubber bands, which are called elastic bands, but which incidentally are inelastic. Now they are on wheels so that they move rather freely, but we learned earlier that this one has less inertia than this one. Now when I pull them apart and stretch the spring between them, the same force acts on both. And let us see if we cannot at once predict what will happen. If we apply Newton's second law to the forces acting on these cars, clearly the big car will have a little acceleration and the little car will have a big acceleration. That's an obvious thing to speculate on. Watch it. I'm going to pull them apart. There is one and the same force acting on both cars, and you will observe that the smaller one gets going the faster sooner. Of course. And so, here is an expression mathematically that describes this. And what do we learn from that remark? We learn that the accelerations are inversely proportional to the masses. The bigger the mass, the less the acceleration. Now more about the second law. Here is a scale on which I hang a weight. And I don't care what the scale reads, it reads something. We say it reads the weight of the body. But I really don't know what that means. Nor did Newton, because as we believe, gravitational forces, the earth pulls on this, stretches the scale. But remember, even Newton said, I offer no hypothesis concerning gravitation, nor do we understand it today. But anyway, this scale reads the weight of this. So I'm going to write Newton's second law saying that very fact. Here it is. F equals mg, where mg is the weight of the body. Now I'm going to accelerate this system upward. And I want you to see what the scale does. Watch it now. The scale read more. And so I have to add here ma. In other words, the scale reads not only the rest mass of the body, but an additional force which was required to accelerate it upward. Let me now start again in the zero position, the system at rest, the scale reading the so-called weight of the body, and let me accelerate downward. Watch it. The scale reads less, and so I write minus ma, mg minus ma. And this tells us a wonderful thing, because if I were to go to the edge of my roof and hold this like this, and then let go of it here, and the whole thing fell down toward the earth, a good question to ask is, what would the scale read during the falling? And the answer is obvious. Since the acceleration downward would be that of a freely falling body, the scale would read 0. So if I should jump off from my tabletop, while I am in flight toward the earth, I am weightless. I am weightless.